Hi everyone, and welcome back to my channel. In the last video we talked about the first two algorithms for scheduling with minimum lateness. We talked about scheduling by Slack. That's where we schedule the more urgent jobs first, and then we talked about scheduling the shortest jobs first. But then with examples we found out that these two algorithms do not work for all cases. In this video, we are going to be considering the third algorithm, which is scheduling jobs with earliest deadlines first. So let's start, with an example. In this algorithm, we are going to be sorting deadlines from the smallest to the largest, and we should note that this totally ignores the length of all jobs. So when we schedule a job, when we sort jobs from the smallest to the largest according to their deadlines, and we also schedule it according to this sorting. So let's say, and I must say that this is also a greedy strategy, and that's because once we schedule the first job with the smallest deadline, we look for the next job with the least deadline also from the unscheduled jobs. So this makes it a greedy algorithm, and it will produce the best solution. That is, it's going to minimize maximum lateness of all jobs. Having explained this, let's talk about how to prove it. Perhaps we could take an example. Let's take an example. Let's say we have, from the last example we took on scheduling by Slack, we would use that example again. Let's say we have job A, length 1, deadline 2, job B, length 4, deadline 4. Right. So when we schedule earliest deadline first, we will have to schedule A first. So we go A, which is length 1, then B, which has length 4. This is B. We see that the overall lateness of this schedule is just a lateness of 1 for B, just as we saw in the last video. This is a lateness of 1 for B. This is the overall lateness for this problem. In the last video, we saw that when we switch the schedule, that's scheduling B first, then A, our lateness is 3, which is higher than a lateness of 1. So let's talk about how to write the proof for this. We are going to be proving this by writing a proof of exchange property. So let's say a greedy algorithm proof of exchange property. Proof of exchange property. Let's say a greedy algorithm. This is our greedy algorithm. And like I said, it goes from the earliest deadline, right? So it goes from, let's say, 1, these are the deadlines, 2, 3 to n. Where this is deadline 1 is less than deadline 2, that way till you get to deadline n. This is saying for short that our greedy algorithm schedules with the earliest deadlines first. If you think about this deadline 1 being less than deadline 2, you could say this is deadline 3, this is deadline 5, this is, so it schedules the earliest. This deadline is earlier than this, so it schedules the earliest deadline first. Okay, now let's also consider an optimal solution, and this is some other solution. We don't know what this is, but let's say this solution schedules deadline 4 first, then deadline 10, then deadline 7, just that way. It doesn't schedule the earliest deadlines first. By whatever algorithm, it schedules in this order: that a job with deadline 4, and that job with deadline 10, and that job with deadline 7, that way. So let's try to illustrate this with a diagram. So supposing this is the schedule for the OPT, that's the optimum. These are the jobs. Uh, you have that, and you have, let's call this I, right? Let's call this I and J, and you have the deadline I greater than the deadline of J. Just like in this example, you have 10 first, then 7. So you have the deadline I greater than the deadline of J. So this is our OPT schedule. So let's think about a new schedule. Let's call it, this schedule is moving towards the greedy. This new schedule, where we are trying to schedule the earliest deadline first, it simply means we are going to switch or exchange I and J. Because the deadline of I is greater than the deadline of J, we switch them. We now have J and I. So we see that here, now we have deadline of J, which is less than deadline of I. What does this imply? This implies that, first of all, for other jobs other than I and J, which we have just exchanged, the other jobs here, the other jobs down here, the lateness do not change. This exchanging of just two jobs only affects the lateness of the two jobs being exchanged, in this case I and J. That's our first observation. And the second observation is that the lateness of job J can only decrease. This is job J. Let's say, like in this example, this is it has a deadline of let's say this has a deadline of 10, this has a deadline of 7, but when we switch it, we see that the lateness of J, the one which comes before the other job, can only decrease. This one decreases. Meanwhile, I, which has the longer or the further deadline, even if it comes late, just like in this example we've given, the lateness is going to be minimal. You can't compare this lateness of I to the lateness of J because the deadline of I is farther than the deadline of J. I just hope that makes sense. Let me use numbers. Let's say, for this example, deadline of I is 10, deadline of J is 7. That means when we do job I, it's possible that by the time we are done with job J, it's later, right? So if we switch J and I, just as we've done here, we find out that we do the job with deadline 7 first, then the job with deadline 10. Giving 10, this gives job I more time, it extends the time at which job I is done because its deadline is further. I just hope this makes sense. So that's the second observation. And the third observation is that the lateness of job I, this is the third observation, the lateness of job I, which is F, finish time, right, minus deadline, is less than or equal to the lateness of job J. Where this is the case, where the deadline of I is greater than the deadline of J. So this means that the lateness of the job J in the optimal schedule is this. This is the lateness of job J in the optimal schedule. And the overall lateness does not increase. Let's use an example. Let's say we have these jobs. Let's say we have, with the optimal schedule, we have a job with lateness 4 scheduled this way with some optimal algorithm, deadline 3 and deadline 2. So now we are going to be using the exchange property to rearrange or to exchange all of these jobs until we get to the greedy. So first off, considering these two, right, we have a job with deadline 4 and a job with deadline 1. which one do you think we should do first? It's the job with the earliest deadline. So it means we are going to be switching this. We are going to be switching this. So we have 1, 4, 3, 2. Switching this do not affect these ones. So we just switch this. So we've done the job with the deadline 1. Between the job with deadline 4 and the job with deadline 3, which do you think should come first? By common sense, it should be the one with the earliest deadline. So we have 1, 3, 4, 2, right? So we keep switching it this way until we get to the greedy, which is 1, 2, 3, 4. And we see that lateness does not increase. In this way, if we schedule our job this way, we see that lateness does not increase. So we can say that with the greedy algorithm, we minimize maximum delay or lateness. We'll be stopping here with this video. In our next video, we'll be talking about another aspect of job scheduling. If you liked this video, please subscribe. It's totally free to subscribe. Subscribe and like, share, comment, and I'll see you in the next one.